Hi, so this video is about going over 11.1, which is about uncertainties and calculations and sig figs. And we're going to be using the study guide as well as looking at this practice test. So let's look at the study guide. The blackboard, I put page 99 and the left side is page 100. So let's go to that. Huh. Okay, 99. Should be around this neighborhood. Go down there a little bit. Okay, 99. So, in chemistry, you have different kinds of uncertainties. So, you have random uncertainties as well as systematic uncertainties. Okay, random uncertainties would be things like, oh, yeah, there's too high of a reading, there's a temperature fluctuation, as you said here, as it says here. Um, so, it's a one off thing. However, systematic error is it happens over and over and over again. So let's just say if the person who's reading it is always misreading it, or the scale is consistently always off by whatever degrees, because let's just say you put the scale right underneath the air duct. That's often an example. Put it often in an air duct, so it's always zero point 0.5 gram off. That would be a systematic error. Okay, so we have to know what they are because how you deal with these errors are different. If it is random error, you want to do more trials. Okay, that's how you can kind of minimize that. But then if you're talking about systematic error, doing repeats won't actually work. You actually have to recalibrate it. Okay, you have to actually fix the system or fix the way that you're doing the reaction. So that's random uncertainty and systematic errors. Now, you also talk about what is precision and accuracy. Precision is how close the things are, your data are together, whereas accuracy would be how accurate they are to the standard value. So if the scale that I earlier talked about, actually, you know what, a better example would be a thermometer. Let's just say if the thermometer is always reading the boiling temperature of the still water, because we all know that boiling temperature of the still water should be 100 degrees. So if your thermometer hits both 100 as well as doing it all the time, then that's both accurate because it reads the accepted value 100 as well as precise. Every single time is 100. Now, if your thermometer only reads it's consistently zero point 0.2 off, so your boiling point ends up 99.8, it's not accurate. It's close though. It's not accurate, but it's very, very precise because it's always like that. Okay. Um, but then if your thermometer is like 80 degrees at one time, 120 another time, it just fluctuates, then it's not precise as well as not accurate. You don't want to use that instrument. So that's the difference between accurate and precision. So here it did talk a little bit more about how you can reduce these random error as well as systematic errors. So make sure you look through this. Now, significant figures. We talked about that before. So first off, you have to figure out which significant figure, which zero is significant. So these zeros won't be significant. Now, this trailing zero would be significant. Okay, so make sure you know the difference. When we spend the whole class practicing on significant figures. Now, after sig figs, you have to, so make sure you look through this. And after sig figs, keep in mind, adding and subtracting have different adding and subtracting have different rules with multiplying and dividing. Adding and subtracting, you're using the least number of decimal place. Okay, you're using the least number of decimal place. So here is two decimal place gives you two decimal place. Whereas multiplication and division, you're using the least number of sig figs. So here's 2 sig figs, here's 3 sig figs. So in this case, you round it to 2 sig figs, so it's a 3.8. In the middle of it, you don't do any rounding. I heard things about like people round things in between, and that's just a bad calculation. You end up double rounding. Your numbers could be very weird, so don't do that. Carry as much as you can, but in between, and then you only round to sig fig at the very end. Now the left side, so absolute percentages and absolute uncertainties and percentage uncertainty. So we talk about that. We talk about in class what they are, as well as how you propagate them, because that's 11.1. So this part here is absolute uncertainty are the ones that you read earlier. So it's usually 0.1 is usually the units will be the same as the unit of the measurement itself. So if you measure 25 centimeter cube, which is really milliliter, your uncertainty is also centimeter cube. To convert that into percentage uncertainty, which you need to be able to do, that's, if you think back to it, that's 11.1, station 3 and station 4, if I remember correctly, the numbers. So regardless, you do your absolute uncertainty divided by your measurement, okay? And you make it to a percentage that will give you 0.4% here for this example. Now, when you're adding things, so let's just say if you do a number of trials, okay, you do 3 trials of measurements, okay? So for this one, it's 2, okay? Let's just say do 2 trials. And then you want to add them up later on. What you need to do is you actually, well, of course, you add up the measurements, but then the uncertainty to propagate that, you actually need to add them together. So for adding and subtracting, you're always adding the uncertainty. You never subtract the uncertainty, because keep in mind, you're making it, the level of uncertainty, you're not sure of things, is getting more and more. So your final, which should be, since you're doing it 2 times, 0.1 plus 0.1 gives you 0.2. Okay? When you're multiplying and subtracting, you need to do 3 different steps. First steps, then percentage uncertainty should be used during the calculation and then convert back to absolute uncertainty. So let's just say in a situation where you're using a scale that's this so many grams, you have to convert this 0.001 gram into a percentage. A different instrument, a pipette, is 0.04 centimeter cube. As you notice, there are different units. So you have to convert them all into percentages. And then afterwards, you add percentages together. Okay? You add the percentages together. So here, you also have 2 more pieces of instrument. So you add them together. And then afterwards, you convert back to the absolute uncertainty. So in this case, since the answer of your measurement earlier, it becomes 108.75. So if the answer is 108.75, you have to convert that 0.8% back to 0.8 or 1% into the same unit. So you have to change it back, which happens to be 0.02. Technically, because it's one degree uncertainty, you have to just put it into, so probably your calculation was like 0.018. So that's how you calculate your absolute uncertainty. Now, if you do total error or percentage error, total error is basically your correct. So this is your accepted value or the corrected value from a given literature. So your accepted value minus your experimental value divided by your accepted value. So percentage error, sorry. So percentage error formula. So for those of you who can't, yeah. So I don't know if you can see it that clearly. So here, percentage error is your experimental value minus your theoretical value. So it's basically the one that's coming from the book or coming from the literature divided by the theoretical value times 100. Keep in mind it's an absolute sign, so which means you cannot have negative number. It's just how off are you. Okay. So that's quite a bit. Now let's take a look at the test, practice test, and see how many questions are 11.1. Okay. So 11.1. So if I look at it, nothing on the first page, nothing on the second page. Now on the so starting question number 3. So 3. Actually, no. Number 6. This is a sigfig calculation, sigfig calculation, sigfig calculation. You notice that we care about sigfigs a lot. Okay, so make sure you do a lot of practice. It's like tying knots. Now number 7 here. This is a little bit more. They want you to actually talk about more in terms of whether you understand how these uncertainties and which one precision and accuracy works. So this whole thing is 11.1. And that's about it. So pause your video here. If you haven't tried the practice test yet, go ahead and try it. And then I will go over the answer with you. Okay? So pause the video now. So I assume you have look over the questions already, done the questions already. So let's look at the answers together. So number 6A. Okay, 6A, you have 120. That's a given value, so it's 2 sig figs. Your answer is 2 sig figs. Here, so you have because your volume of the earth, they gave it to you as 1 sig fig, so your final answer has to be 1 sig fig. And since now I know that it is a conversion. However, even in conversion, you still have to use the original given value. Since the original given value is 1 sig fig, you still have to round it to 1 sig fig. So that's the reason why. Okay, which set of data is more precise? So if you look at that, now 1A and B, it's pretty widespread of data. Set 1, all of them are much closer together, so in this case it's more precise. Which one is more accurate? So in this case, let's look at that. Your accepted value or the literature value is 48. So in this case, these are really close to 48. This is all over the place, and none of them ever hit 48. So A would also be more accurate. Okay, closer, it's more closer to it. Explain whether these could be made more accurate by conducting more. Now that really depends. Okay, because more trials increase precision, not accuracy. So in this case, yeah, you already have a lot of um, you already have a lot of data. So it's because it's about your because you're talking about can you increase accuracy? No, accuracy you have to improve by a different method of doing the experiment. Okay, now that's about it in terms of 11.1. Based on this practice test. Again, if you haven't finished your packages on the station on 11.1, try to do that. And if you have any questions, I'm walking around. Make sure you ask me, okay? Good luck and move on to a different station too, okay?